speaker graciously agreed to move his talk to Tuesday to help us out. We've got Ian Leary from University of Southampton who will talk about
I can't remember.
some stuff, yeah, some great mathematics. Take it away.
Thank you, Graham. Thank you, everybody, for allowing me to be here and for allowing me to give a talk. It's my first visit to the Fields Institute. Yeah, yeah, that looks a nice way to spend the afternoon. But yeah, so I feel a bit of a fraud here, really. I don't really have anything new to say about polyhedral products, and the new things I was hoping to talk about, I think we've decided there isn't enough new to be able to do anything with them anyway. But anyway, so I'm going to talk about, it's probably a good last thing in the afternoon talk anyway. Oh, yeah, there's sort of open problems, but they're horrible, famous, notorious open problems, so I didn't want to mention them in the problem session because they're not the sort of problem you should think about, really. But anyway, polyhedral products do come in. So yeah, polyhedral products, I mean, I'm a group theorist. My favorite polyhedral products are, I mean, again, Taras Panov mentioned them yesterday. So we've got the circle and a point. That's one. And this yields right-angled Artin groups. Maybe I'll abbreviate that as RAGs. And the other one is, I guess I want an interval and its endpoints. And maybe the interval is going to go from -1 to 1, because I'm going to swap the endpoints as well at some point, and that just feels more natural to have an interval whose ends are, I don't know. Graham thinks it's a reasonable thing to do. But maybe I shouldn't call it I, because I usually goes from 0 to 1, doesn't it? It's still an interval, yeah. It's a more interval or something. And this is going to give us right-angled Coxeter groups. And so time's passing quickly, isn't it? We've got either a graph, a simple equals simplicial graph, or its flag complex. So a flag complex, it's clique complex. And again, we know why we want to take flag complexes from a group theoretic point of view. Again, as Taras Panov said yesterday, a family of elements of different groups commute if and only if any two of them commute. So if we've got the edges of a simplex, we're going to put the whole simplex in. So that's why we only want to consider flag complexes. So I'm going to write A sub gamma for a graph, but I'll probably have A sub L is my letter for a flag complex. I don't know. So this is the fundamental group of the polyhedral product for the circle and the flag complex L. And again, we could write out generators and relations. We've got the generators V, the elements of the zero simplices of L. And the only relations we've got are that V and W commute if VW is an edge. Okay, and then the other one, well, I'm going to write down the right-angled Coxeter group, and I'm going to start with this. So we're going to have, again, just the vertices of L, and then we're going to have that each vertex corresponds now to an element of order 2, and then this commutation relation, we could also think of that as VW squared. But no, let's just stick with it being a commutation thing. Okay, and so obviously there's a surjective homomorphism from here to here where we sort of forget what the, we add in the extra relations. That's given us a surjective homomorphism from this group to this group. I haven't told you how to interpret this group in terms of this thing here. The thing is, we don't quite want the fundamental group of this thing. So cyclic 2 acts on the interval by x goes to minus x, and that swaps the two ends. And so then if everybody's been using m for the number of vertices of the simplicial complex, haven't they? So cyclic 2 to the m acts on the polyhedral product by flipping the coordinates separately. We've got as many generators as we've got coordinates, and we swap the coordinates separately. So then that gives an action. Well, yeah, I guess I want to say then, so WL is the group of, so again, we could define the fundamental group. So yeah, what I really want is, we've got pi 1 of this polyhedral product, and then we've got the Coxeter group, and then we've got the quotient. Yeah, but I want to say that in a more accurate way. So the way I'm going to say that is we have, this gives us 2 to the m self-maps of this space. The fundamental group is the group of deck transformations of the universal cover. So the group of all self-maps of the universal cover that map down to the identity map on this. So the whole Coxeter group is the group of, so it's the group of self-maps of the universal cover. I don't know. I haven't got enough notation for anything, have I? So not just the ones that map down to the identity, but the ones that map down to the action of any one of these elements. Yeah? That project down to some element of C2 to the m acting on the polyhedral product. Right, so again, we could have gone to RP infinity relative to a point, and then we could have looked at the universal cover of that, and then we could have used this nice theorem about the infinity sphere and the 2 points, the infinity sphere and the pair of antipodal points. The infinity sphere is contractible, and cyclic 2 acts freely on it. And again, as Tara said yesterday, we can replace that infinity sphere by any other contractible space. But the catch is, if when we've replaced it by a finite dimensional contractible space, cyclic 2 can't act freely on it anymore. We've got this fixed point in the middle by the P.A. Smith theorem or something. So we're not making a universal cover of a KG1. We've not started with a KG1. This universal cover is called the Davis complex, same Davis as usual in these talks. So this group isn't torsion-free. It's not a split extension in general. I mean, you can see when it's going to be split. Let's do the two simplest examples. If we have just 2 points for L, then we've got 2 generators of order 2 and no relation. How am I going to get, where do I get my, oh yeah, my polyhedral product's a square, isn't it? Great, my polyhedral product is the boundary of a square. And one of my 2 generators is acting like that. And one of my 2 generators is acting like that. And when I pass to the universal cover, I'm getting the line, and one of the lifts of A is acting there, and one of the lifts of B is acting there, and their composite is a translation. So this is the infinite dihedral group. Notice that there was nothing in the middle of the square. There's no cyclic 2 cross cyclic 2 in this group, right? Whereas if we did L equals 2 points joined by a line, the picture looks the same, but now I'm coloring in the square. Now it's its own universal cover, and I've just got these 4 elements, and now we've got cyclic 2 cross cyclic 2 instead of infinite dihedral. You want me to stop now? No. Yeah, so for various reasons, I mean, some things are known about Coxeter groups. So, for example, every right-angled Coxeter group, so one of these Coxeter groups, is linear over the integers. So that it has a faithful finite dimensional. In fact, I think you need twice as big a dimension as the number of generators or something for the natural choice. I can't remember. It's either twice as many or exactly as many. Anyway, this group embeds in the general linear group over the integers. And you might want to know that the Artin groups do as well. And one of the simplest ways to do that is to embed the Artin group in the Coxeter group. Right, so the one generator Artin group is the infinite cyclic group. We can embed the infinite cyclic group in the infinite dihedral group. Right, that's fine. And then we could, so the right-angled Artin group equals the graph product of infinite cyclic groups. We could embed that in the same graph product of infinite dihedral groups. Yeah? Here I'm thinking, you know, I guess I've got a third instance, haven't I? Instead of just having cyclic 2 as my groups that I'm taking the graph product of, I'm now taking free product of 2 cyclic 2s. Okay, so that's fine. That does. And so this equals a right-angled Artin group, a right-angled Coxeter group, but it's for a different complex. It's the right-angled Coxeter group for a new complex. So if you think about it, this was the 1 generator right-angled Artin group. This is the 2 generator right-angled Coxeter group where the 2 generators are not joined to each other yeah? So what we've done here is we've replaced our original, if we want to write this as a right-angled Coxeter group, we've replaced our original L with something new that has 2 new vertices for every old vertex. And the 2 new vertices, we're going to say we're going to replace V by V1 and V2. And then, hang on, no, let's call them V primed and V double primed. Yeah? And so then, if we've got a simplex over here, V1, VI1 up to VIK, span a simplex, then that's going to be a simplex if and only if the same thing for any choice of primes or double primes. Yeah, you see what I mean? So you call this the octahedralization. We've replaced each vertex of our original L by 2 copies. We've replaced each edge by a square. Yeah, maybe I should draw this more. So we replace V by two copies, V and V prime and V double prime. We replace the edge VW by the square V primed W primed, yeah? And each triangle will get replaced by an octahedron, yeah? So we're making a new simplicial complex with twice as many vertices. That's essentially another way of looking at this, embed the graph product of Zs in the same graph product of D infinities. But this same graph product of D infinities, we can express it as a graph product of cyclic 2s over this more complicated simplicial complex. Right. What's wrong with this? Come on, I mean, oh no, it's true, it does embed. What's unsatisfactory about it? The problem is that it's not finite index. Yeah? I mean, well, in this example, it was finite index, it was index 2. And if we do Z squared in D infinity squared, it's index 4. Yeah? It looks good, but it's not finite index in general. So let's think about what we're doing with the free group on 2 generators. So the right-angled Artin group for these 2 dots, we're going to embed it in the right-angled Coxeter group for these 4 dots. I'm not sure which 2 dots correspond to which one of these dots, but yeah, we've got, yeah? So this is the free group on 2 generators, and this is the free product of 4 copies of cyclic 2, yeah? Now, if you think about, I mean, you don't need to believe this argument, but what's the Euler characteristic of this group? It's, well, yeah, it's 1 minus 2. It's minus 1 is the Euler characteristic of this group. What's the Euler characteristic of this group? I'm afraid I'm going to have to do it as a star like that with a C2 at each end. Yeah, so the Euler characteristic of this group is a half plus a half plus a half plus a half plus 1 minus 1, 2, 3, 4. Right? So that correction, everybody believe that calculation? Yeah. The Euler characteristic of this group is also minus 1. Right? So there's no way that this can be a finite index subgroup of this group unless it's index 1. Yeah? So either it's infinite index, which is what actually happens, or the groups are isomorphic, which of course doesn't happen. Right? So this is the wrong Coxeter group. So what, I mean, Davis, Januszkiewicz found a finite index embedding. Right, so what did they do? Well, they went back to this polyhedral product. Again, I might not get time to say anything else, but if I've explained the Davis-Januszkiewicz embedding, I'll have done something good today. If I get it right. Right, so that's our first, that's the one that corresponds to the right-angled Artin group. And oh, no, sorry, yeah, I want, somehow this with a reflection in the middle is what corresponds to the, no, what should I do? I want to put dots on the end to indicate that they're, but somehow I've also got the reflection. Let's do the reflection. We could use red, couldn't we? No, let's do a dotted line for the reflection. That's the one for the right-angled Coxeter group. Yeah, so what we're going to do is modify this slightly. We're going to have a reflection that way. Yeah. Right, so then when I've got that reflection, I can draw it like that. And I've got two ways to unfold this. Yeah. If I unfold it, yeah, I think if I unfold it here, I'm going to get the circle back. But I can unfold it at one of the two ends. And I think I've messed up the picture because I want to put that end in the middle, I think. I want to put that end in the middle. So I want to unfold about this one, but not about that one. Is that right? Votes? No, sorry. I want to unfold about this one, but not about that one. And so I can either get to that picture by, and that's somehow I'm taking an index 2 subgroup where neither this reflection nor this reflection is in my subgroup. Or I can unfold this way and I can get a picture like this. Now, unfortunately, I just chose to put my dots in the wrong place. I should have put my dots in the middle because that's where I want them now. But anyway. Okay, so what does this correspond to in polyhedral product land? So we've got cyclic 2 to the m acting on S1 point to the thing. And then I've got two homomorphisms from that onto C2 to the m. And one of them is going to have kernel the right-angled Artin group. The other one is going to have kernel a different Coxeter group. Right? Now this Coxeter group, it's going to have two new generators for each old generator. So as before, we're going to send V to two new generators, V primed and V double primed. And the relations, the commuting relations between the V primes are going to be just as they were. But the product of these points is going to be fixed by pretty much everything. The only thing that won't fix this point is this reflection. Yeah. So what does that tell us? It tells us that the V double primes all commute. So W primed equals 1 for all V and W. And it also tells us that V double primed is going to commute with W primed, except if W equals V. Okay, and then the commutation relations between the V prime and the W primes are if and only if the same thing holds for the V and the W. Yeah, so this is a different Coxeter group. Let's see what we're getting for let's just sanity check whether we've got the right thing here. I think here we've got our two original ones. We've got the two new ones that commute with each other, and each of the new ones commutes with one of the old ones, but different ones. Yeah? So I'm getting sort of cyclic 2 cross cyclic 2, free product over cyclic 2 with another cyclic 2 cross cyclic 2, free product over cyclic 2 with another cyclic 2 cross cyclic 2. Okay, so this Coxeter group now, the Euler characteristic is minus a quarter, minus a quarter, minus a quarter. No, sorry, a quarter, a quarter, a quarter, minus a half, minus a half. That's 1 minus a quarter, isn't it? Which is a quarter of minus 1. Right, so this group could contain this group and this group as index 4 subgroups, and it does. Right, so that's the Davis-Juniskiewicz embedding. This picture with the circle and this picture isn't in their paper, but I'm sure this, anyway. Okay, so I said I was going to talk about, the index is 2 to the m, the number of, yeah, and they have the same index. So they're sort of commensurate groups, commensurate of the same index, which is sort of extra property. Yeah, so, yeah, it's the right-angled Artin group and the naive attempt at finding a good right-angled Coxeter group for it to embed in are both index 2 to the m, where m is the number of vertices, in the correct right-angled Coxeter group to embed in. Yeah. I said I was going to try and talk about, this was the last board I wrote on, wasn't it? That's terrible style. Erasing that one next. Never mind, I've done it now. I said I was going to try and talk about the two families of counterexamples to the Eilenberg-Genea conjecture. So the Eilenberg-Genea theorem 1957, if the cohomological dimension of G is greater than or equal to 3, then there exists a KG1 of same dimension. And it tells you a little bit about the low dimensional cases as well. Stallings and Swan in the 1960s late 1960s, CDG equals 1 implies G is free. So CD1 is the same as having a one-dimensional KG1. Okay, so putting this together plus a little bit that I didn't say, the only possible case where cohomological dimension and the minimal dimension of a KG1 might differ is when the minimal dimension is 3 and the cohomological dimension is 2. Now, I haven't said anything about how you prove this, but in fact, what you do is you look at the universal cover of a skeleton for any model for EG, and then because you've taken a skeleton for EG, it's only got one non-zero homology group, the top one. If you're close to the cohomological dimension, that top homology module is a projective module. You can change it to be a free module by some trick. And because you're in the range where cohomological dimension -1 is at least 2, then you've then got the Hurewicz theorem to say any homology class you want to kill, you can do by attaching a cell. Yeah, so the Hurewicz theorem is what fails when you try and do this for 2. And what you can say for two-dimensional group, you know, CDG equals 2, or less than or equal, let's say, yeah, to make it true what I'm about to write, is less than or equal to 2, if and only if G acts freely cellularly on some acyclic two complex. Right, so you can't promise yourself that you've got the 2 skeleton of a KG1 of the right, but I mean, the thing is, if you're prepared to possibly add too many cells and then you're going to add some H2 and you're going to have to add 3 cells, you can get the fun. Yeah, all right, sorry.
What if you see weaker hypothesis, bigger homological dimension?
It's a lot. No, it's I mean, it's definitely false. I mean, for example, this is cohomology with arbitrary coefficients. Yeah, no, yeah, thanks, Alex, for mentioning that. No, I mean, there are things like the Higman's group, 4 generators, 4 relators. It's ordinary homology is the same as the homology of point. There are lots of acyclic groups. Yeah, no, this is cohomology with arbitrary coefficients. So I mean, even like the Klein-Bottle group is a 2-dimensional group because, you know, the top homology of the Klein-Bottle is 0, but if you use twisted coefficients, it's not. Yeah, so no, you definitely need arbitrary coefficients to your cohomology. Now, trivial cohomological dimension, yeah, it's an interesting invariant, but again, it's nice for Artin groups and things. But anyway, but yeah. Okay, so okay, so now again, I might not be able. Well, let's see how we get on. So suppose L is an acyclic, but not contractible 2 complex. Oh, and of course it's a flag simplicial complex as usual. Yeah. Do we want an example of such a thing? Poincare homology. Yeah, we've got Coxeter's drawing of the sculpture outside, the 120 cell. Yeah. So there's a subgroup of S3 of order 120. So it's it's a group of order. It's got A5 as a quotient, and the kernel is cyclic 2. The CELOF 2 subgroup is quaternion. I mean, you might prefer to think of it as the special linear group of 2 by 2 SL2 over the field of 5 elements. Anyway, there is a group of order 120, which is perfect, and which is a subgroup of S3. If you look at the cosets of that space, just take the S3 mod the cosets. That is the Poincare homology 3 sphere. Okay, so then if we take let's go back to the sphere. We've got 120 points or subgroup elements. Take the Voronoi cells of them. They turn out to be dodecahedra. And so if you take out the interiors of the Voronoi cells and then quotient by the group, you're obviously getting something acyclic because you've taken something out of a homology 3 sphere. I don't know. I promise you it's right. I mean, the other way you can make it is you can, and again, I think this is just coming from the same thing. If you think about, you can think of it as we've done some identifications on the boundary of a dodecahedron. And so if you take the complete graph on 5 vertices, now there are 24 5 cycles, but the inverse of a 5 cycle and a 5 cycle give the same way to attach a pentagon. So there are 12 ways to attach a pentagon to this. they fall into, oh, and they're a single conjugacy class under symmetric 5. They're two conjugacy classes under A5. So if you take one of the two A5 conjugacy classes and attach those 6 pentagons, that's a way to get this same space, the the Poincare homology sphere. Okay, so it's an acyclic 2 complex, and it's not contractible. Its fundamental group is order 120. Right, so then let's look again at this this polyhedral product. Oh, and of course, what's the fundamental group of this? It's the commutator subgroup of the right-angled Coxeter group. I mean, I guess we know it's the kernel of a map from the right-angled Coxeter group to C2 to the M. But of course, there were only M generators, and they each had order 2. So that obviously has to be the complete abelianization. So the fundamental group of this thing is the commutator subgroup. What does this thing look like locally? Well, again, if we do a simpler example, we do the sort of 3, where one vertex is not connected to anything and the other 2 are. This looks like a sort of T-trolley. Yeah, so we've got the where the, you know, the bit that we put the T on and the bit we put the dirty cups on there, they're filled in, but the rest isn't. Yeah, so we filled in the squares corresponding to this edge. Yeah. Okay, so the link of each vertex here is exactly a copy of this. So the neighborhood of this vertex is a cone on this. Yeah, and the vertices are all identical. There's 2 to the M of them. So the link of each vertex is a cone on this, right? Oh, and this was 1-dimensional, this is 2-dimensional. Okay, so here we have a case where L is 2-dimensional. So this thing is a 3-dimensional thing made out of cubes. Again, if we want, we could subdivide everything into smaller ones so that we've got fixed points in the middle. Right, so then we could consider instead just the subcomplex of things that are far from the vertices. Right, so in this case, it falls apart. Yeah, when I do this one, I've fallen it apart by cutting out the neighborhoods of the vertices and pushing back onto the skeleton of the thing. But if this L is acyclic, it doesn't fall apart. In fact, it can't fall apart because when you attach a cone on an acyclic space, you don't change homology. Yeah, so when L is acyclic, if we just take the bit shaded in red, so you know the cubes of the subdivision where you cut each n cube into 2 to the m, that subdivision. If you just take the cubes that don't contain any vertices of the original, that's what I mean. Yeah. That space has to be acyclic, and of course it's 2-dimensional. So the red bit is acyclic and 2-dimensional. And its universal cover, of course, or not its universal cover, sorry, its pre-image in the universal cover of the whole thing is also acyclic. Oh, I said this one was acyclic. I was lying. We should have taken the universal cover first. We should have taken the universal cover first. There we've got more vertices, but they all look like this. And each vertex, each vertex is still, a neighborhood of it is a cone on any cyclic thing. Therefore, the red bit of the universal cover is acyclic and 2-dimensional. Graham's frowning. sorry, when L is L is two-dimensional. L is two-dimensional, so this cubey thing is three-dimensional. And yeah, so then this, yeah. I would have done if I'd not been so slow, but I'm not going to say Whitehead. No. So this group, WL, has cohomological dimension less than or equal to 2, and in fact it's obviously exactly 2. It can't be lower. Yeah? So this group has cohomological dimension 2. We don't know a contractible 2 complex on which it acts freely. So this group is probably a counterexample, right? There are better attempts at counterexamples or more complicated ones. So yeah, if you want to mention Whitehead, we need the other family of counterexamples. And again, I wanted to say more about this. I haven't even mentioned Taras's fantastic theorem about the commutator subgroup. But anyway, so take the same L. Oh, let's move to another board, shall we? What time did I start? Slightly late. No? 5 minutes, great. Okay, so take same L, and we're not going to take, the thing is we're not taking the group AL this time. But we're going to look at that space you know that, and again I'm just repeating bits of Taras Panev's talk yesterday really, but anyway, this is an abelian group, so there's a group operation from this to S1. Yeah, where we just multiply all the coordinates together, and so that gives us a map from here to S1. So that gives us a homomorphism from the right-angled Artin group onto Z, or if you like, the right-angled Artin group of a point. Yeah, corresponding to the unique map from the simplicial complex L to a point, where we just send all of the vertices to the one point. Right. If you take the universal covers, you've got the universal cover of this thing, which gets called XL, mapping to the real line. Yeah. And it turns out this kernel is the group we want to look at now. Okay, and this is called the Bess-Wiener-Brady group associated to L. And again, you can look at other homomorphisms to Z, and I think this might be the sort of thing that might come up in Alex's talk. Is it? Or no? Okay, it's something that lots of people have thought about, you know, cohomology and homology of these types of kernels. Anyway, it turns out for this same L, for L with the same properties as before, although the right-angled Artin group here has got Z cubed inside it, so it's definitely got cohomological dimension 3, and the cube complex is 3-dimensional. This thing is 2-dimensional again. But again, this whole space is a 3-dimensional contractible thing it acts on. And again, there's some sort of argument involving the acyclicity that gives you a 2-dimensional acyclic space that this group acts on. Again, maybe with BBL, again, looks like, well, acts freely on some acyclic 2 complex. And again, the argument that Besfino and Brady give here, you take the inverse image under this map of any point, and then that's a subcomplex that the whole Artin group moves things up and down, but this kernel doesn't move things up and down by definition. It's the things that are trivially on R. So the kernel preserves this level set. And that turns out that level set is acyclic by some Morse theoretic argument involving the fact that L was acyclic. So it's another group where we have an acyclic 2 complex, but is not known to act on any contractible 2 complex. Act freely on any contractible 2 complex. Okay, and this is the one that Besfino and Brady spent a long time trying to prove this was an Eilenberg-Genaer counterexample. And the best they got was this theorem that if the Whitehead conjecture that every subcomplex of an aspherical 2 complex is aspherical, if that holds, then this group is a counterexample to the Eilenberg-Genaer conjecture. Right, so one of the 2 big conjectures is false. I'm sure Eilenberg-Genaer is false. I've got no idea whether Whitehead is true or false. I was going to say something about Taras's thing being used to show that somehow that example's more basic than this one, but maybe I don't know. I better stop now, hadn't I?